Right, section 7.3 is on quadratic forms. So it's basically a little bit of an application of diagonalization. It's another application of diagonalization. So suppose a1 up until an are fixed constants, then the expression of the form is a real valued function of the n variables x1 up until xn. And that is called a linear form in Rn. Okay, thus all variables in a linear form occur to the first power, and there are no products between the variables. A quadratic form, however, is a function where you have squares of the variables, and then you have the cross products between the variables xi and xj for all indices I and j not equal to one another. Now, right, so the terms of that form there, they are called cross product terms. Okay, so that's what's known as a quadratic form. So here we've got two examples of quadratic forms. These are well known functions in R2. So there we've got a quadratic form, and we've got a quadratic form in three variables. Obviously, just one note that the term xi, xj is the same as the term xj and xi. So we combine these terms to avoid duplication. Okay, so that form there as an example. We can go and take that function and express it as a product between matrices. We've got the two, the one column, the column vector x1, x2, which we can write as a transpose, multiplied by a matrix where the entries are comprised of these coefficients. And then we've got the column vector x1, x2. Now one can go and see that if you multiply that matrix out, you get this function here. So it's possible to write all these quadratic forms as a product of matrices in that particular form. Okay, so just to note that a general quadratic form in R3 would typically be expressed as again a product of, now you've got three variables, so you've got your row vector with three variables. You take the transpose of that vector, which is this vector here, and then you've got the coefficients, or the coefficient matrix. Right, now if A is a symmetric n by n matrix and x is an n by 1 column vector of variables, then this function that we have, remember, we have the transpose of x, which is a row vector multiplied by the matrix A, which is now the matrix comprising of the coefficients of your quadratic function, multiplied by the column vector x. That function is called the quadratic form associated with A, with A being the matrix. Now you can also just write this in terms of you can interlink between the dot product and matrix multiplication. We can write this matrix multiplication as just a dot product between two vectors, one row vector and one column vector. Okay, and the dot product you can is commutative, so you can switch the two around there. Right, so the next question, they just ask us to express the following quadratic forms in that matrix notation there, where A is a symmetric matrix. Right, so there we've got our first function, and we need to write that in matrix notation. Right, so what you can do is you can let A, now A is going to be a 2 by 2 matrix, and what you want to do is you want to let your vector X be, that's a column vector, so that's going to be the column vector of your variables. And what you want is you want your function, you want that function to be expressed in the form right. So this little part here, you can quickly go and find an expression for that. So we know it is going to be basically the matrix A. We're going to take, we're going to multiply that with, the row vector. Okay, and we can write that out. Right, so multiplying the first row vector with the matrix A, we get another row vector, and that is then equal to. Right, so there we get that, and therefore what we need is, we need A to be 4. Right, we need D to be 6. And we need basically C plus B to be equal to minus 7. So we need C plus B equal to minus 7. Now remember, the matrix A needs to be symmetric. So C and B needs to be the same, right? Right, now as A is symmetric, so we need basically, we need C and B to be the same. So C needs to be minus 7 over 2, and B needs to be minus 7 over 2. Right, so there we have the expression of my function in the form X transpose AX. Right, where X is this vector here, or X transpose, and there's the vector X, and there's A. Right, so the procedure is quite straightforward. So that takes care of that one. This one I'm going to leave as an exercise. So there you've got 3 variables, so your vector X is going to be comprised of 3 variables. And then you want to find the 3 by 3 matrix A, a symmetric matrix. Right, so what you need there is right, because it's symmetric, you need that to be the same. So then you are going to solve for A, B, C, D, E, and F. Right, so you should then be able to solve A as the following matrix. Let's see if you get this. 1, 3, 2, half, minus 2, minus 2, half, and 5 over 2. Right, now where does the application of diagonalization come in? If we have a function in quadratic form, we can actually make it simpler or make it more manageable to work with by eliminating the cross products. If we go back to our previous example, what I actually want to do is I want to get rid of these terms. Okay, I want to somehow get rid of these terms. If you get rid of those cross terms, the form of that your function is in is much simpler to work with. That is what this change of variable in a quadratic form is all about. So we are going to change a variable and convert the quadratic form into something that's simpler. So again, many of the techniques for solving the problems we are interested in are based on simplifying the quadratic form, that form, by making this substitution. So these variables, the x variables, are in terms of the new variables that you introduce, y1 up until yn. And P is a matrix. Now, if P is invertible, then xpy is called a change of variable. So you want P to be invertible because it's going to play a role in diagonalization. If P is orthogonal, however, then, in other words, P's inverse is its transpose, then that P is called the orthogonal change of variable. Right, so the principal axis theorem basically just states that if A is a symmetric n by n matrix, then there is an orthogonal change of variable that transforms the quadratic form into this quadratic form where the new quadratic form has no cross product terms. Specifically, if P orthogonally diagonalizes A, then making the change of variable in the quadratic form yields this new quadratic form there, where these lambdas are my eigenvalues of A corresponding to the vectors that form the successive columns of P. So let A be a symmetric matrix with eigenvalues lambda 1 till lambda n, and let P orthogonally diagonalize A. Right, so what we do is we create a new variable, or change a variable. Alright, so you set x as that column vector and y as that column vector. Right, then you do this substitution. Remember, we said that x is that, so what we're going to do is we are going to do that substitution there, so that becomes transpose A there we go, right, and that becomes Y's transpose P's transpose A, P, Y, right, and that then becomes Y's transpose. This part here becomes the diagonal matrix, Y transpose, okay, and that is pretty much, so it's that vector there, and then we've got this vector here, and then in between we've got the diagonal matrix, which is pretty much composed of all the eigenvalues on the diagonal. So multiplying that out, that then becomes lambda 1 y1, lambda 2 y2, and you're going to go up until lambda n y n. and then you've going to multiply that with that vector there, the dot product, and that is going to be lambda y1 squared plus up until lambda yn squared, and that's lambda 1 up until lambda n. Okay, so basically, as one can see, one has basically eliminated all the cross terms from the original quadratic form. So this brings us to the next example. Here they ask us convert this quadratic form into a quadratic form without cross product terms using an orthogonal change of variable. Right, so we are interested in this part, in the first part here. We are going to look at right, so we want to go and investigate this little, we want to get rid of that term there. Okay, so first of all, we know how to write this in matrix notation, right? So what we're going to do is we need to write that in the form, we need to write that in this form here. And we already know how to do that. Right, so we can go and determine what the symmetric matrix A needs to look like, right? So you can solve for A as that, and you can write that quadratic form as a product between matrices in that form. And now the change in variable that we want to make is we want to, right, so we want to change the variable, but in order to do that, the variable that I want to change is I want to change it into that form there. Right, so I'm going to choose, what I want to do is I want to change P, I want to go and find P. So essentially I want to go and diagonalize A, symmetric matrix. I want to go and orthogonally diagonalize A. So we want to go and find the eigenvalues of that matrix. Okay, so we are going to take this matrix and we are going to we're going to look at the eigenvalues. All right, so that is going to then become lambda minus, that is going to become minus, right, that is going to become minus, and that is going to become lambda minus. Okay, so we want to find the determinant of that matrix to find the eigenvalues. So that's going to be it's going to be lambda multiplied by this, okay, and then it is going to be minus 4. And what you're going to do then is you're going to take this and you're going to set that equal to 0, and then from there you get, okay, and then from there you can go and factorize that as lambda minus 6, lambda minus 1, and so the eigenvalues become Eigenvalues occur where lambda is equal to 6 or lambda is equal to 1. So now we need to just go and find the basis for each eigenspace. So the eigenspace, so the basis for the eigenspace for lambda equals 6, you determine that by, right, so that's going to become lambda equals 6, so it's 1, 4, minus 2, and then you go and reduce that to find the null space, and you get 1 minus 2, 0, 0, and that corresponds the basis is going to be the vector. The basis is going to be the vector 2 and 1. That's going to be the basis vector. Now, to orthogonally diagonalize, we need to find an orthogonal basis, or an orthonormal basis. So we need to normalize the basis, right? So with the vector, if we go back, this vector is not a normal vector, or it's not a unit vector, because its norm, what is the norm of that vector? So if you look at the norm of this vector here, it's going to be the square root of right, so the orthonormal basis is going to be pretty much this here, and it's going to be the normalized vector. So that's going to be 2 square root 5 and 1 square root 5. Alright, so the basis for the eigenspace for lambda equals 1, that's going to be minus 4 minus 1 minus 2 minus 2, and that you're going to reduce to that. And so alright, so that corresponds to the linear system 2x plus y equals 0. So what we can do is you can go and parameterize the variable y, and so your vector is going to become that. Right? Right, so what is the norm of this vector? The norm of this vector is going to be the square root of right, so the orthonormal basis is going to pretty much be, it's going to be the set containing the following vector. Alright, so there we've got the two vectors from the two respective bases, and what we're going to do is we're going to form our matrix P. And then the second column is going to be And the matrix P orthogonally diagonalizes my matrix A. And recall that the first column corresponds to lambda equals 1 and the second column corresponds to lambda equals 6. So your transformation then becomes, okay, so that's going to be matrix A, and then what I do is I replace X with that part there, and I replace the other part there. And then that's going to become Y's transpose, P's transpose, A, P, Y. And what's going to happen to this matrix here? That we know is going to be diagonalized. So that's going to be Y transpose. And that is going to be the diagonal matrix. Right, so that's going to be this matrix here. Now remember what A was, and we can go and do that replacement. Right, now remember the matrix in the middle, this whole part here, which includes the transpose of T of my diagonal of my matrix P. That part there is the diagonal matrix where this eigenvalue corresponds to that column, first column, and that eigenvalue corresponds to the second column, right? So basically, if we go back, we can then just go and replace that with this matrix here. Okay, and the variable y, let's call that something else. Let's call that x prime, y prime. Just see what this looks like. That will then be x prime squared plus 6 y prime squared. Okay, so that's a nice little application of diagonalization. We can take a function in a quadratic form and we can go and write it in a simpler way by eliminating all the cross products. Right, next up is definition of a conic section. A conic section or conic is a curve that results from the intersection of a double napped cone with a plane. Right, so there's a cone and let's intersect the cone with a plane. There's a plane, and basically what we could have here is we could have a situation where the plane is nice and parallel to the one of the planes in this case, right? So if it's that case there, then obviously we've got an intersection here, and the intersection is pretty much a circle. Or you could say have a situation where you are intersecting it in that particular way, and then you're going to have a slightly different scenario here. You are going to have an ellipse. Right, so in that case you have an ellipse there. Right, so you could get a situation again. I mean, you can get quite a few variations here. If it intersects it that way, then we are pretty much dealing with a parabola. So looking from that angle, you can clearly see there we've got the parabola. Or we could also have a situation where we get an intersection of the following form. Or you could have an intersection of that form, say, and you get an actual factor in hyperbola. Right, so that's what a conic section is. Right, now a conic section normally has the equation of that form, and that is basically a quadratic form. So our diagonalization principles can come in quite handy here. And that represents a conic section. Now, also just take note that at least one of the A, B, or C's is not 0. Now, in this equation, if in the equation of a conic section the linear coefficients are all 0, in other words, your equation looks like that, then the equation represents a central conic. Okay, a central conic is said to be in standard position if B is 0, in other words, if it has no cross product terms. And these are examples of central conics in standard position. So if that cross product term is 0, then you've got this neat little structure here where it is the conic section. If you project it on the XY plane, then it's going to have its middle point in the center, at the point 0, 0. Okay, now all central conics can be written in this particular form. Now, if A is diagonal, the conic is in standard position, and if A is not diagonal, the conic is rotated out of standard position. Right, so if we look at a conic that is rotated out of standard position, in other words, if A is not diagonal, and obviously then we would like to know, rotate this conic so that it is in standard position, because then it's easier to work with. The procedure for doing so, suppose we want to rotate the conic to be in standard position, but we're also interested in finding the angle of rotation. Then what we're going to do is we're going to find a matrix P that orthogonally diagonalizes A. And what we want to do is we want to make sure that the determinant of P is 1. Now recall when we looked at transformation matrices, remember that the matrix that rotates a point xy through theta, we said that the transformation matrix that did that, we derived it as that matrix there. Now with a conic section, we want to transform the coordinate system. We want to rotate it from where it is to the standard position. So that's where the following comes in. Now the first column of P is the rotated x-axis, and the second column of P is the rotated y-axis. So what we want to do is we want to let P be this matrix here. And remember now we derived the matrix that orthogonally diagonalizes A, and we just want to ensure that this matrix has determinant 1. And also this matrix has determinant 1. So basically we're going to use that matrix to find the angle theta of rotation by simply solving by simply taking the P that I obtained there and using this to solve the angle theta. Right, so we can then find the angle theta counterclockwise through which the standard axes have been rotated. So perhaps it's good to just look at an example. Here they ask us identify a conic section represented by this particular equation. by rotating axes to place the conic in standard position. And then we're asked to find an equation of the conic in rotated coordinates and find the angle of rotation. Right, so this quadratic form, we've already worked with that. We took in the previous example, we took this and we went and we wrote that in a different form by eliminating that term. Right, so recall we wrote that as we introduced two new variables, x prime and y prime, and we pretty much wrote that expression as the expression on the right hand side, which is equal to 6. Okay, so basically x prime squared over 6 plus y prime squared is equal to 1, and that's the equation of an ellipse. Right, so we've identified the conic section by rotation. So now we're asked to find an equation of the conic in the rotated coordinates, which we've just done, and we need to find the angle of rotation. Right, so we need to find the angle of rotation. Right, so we take that matrix we derived, and remember now we just need to check the determinant of this matrix is 1. So we can clearly see there the determinant of that matrix is -1. So what we're going to do is we're going to swap the columns, right? Okay, and that is still going to give me, it's still going to diagonalize, and that is clearly, that's clearly has determinant 1. Right, so what we want is we want to equate this, we want to equate this to this here. Right, so we've got that situation there, and then it's just a question of solving those angles, and so from there we get that cos theta is 2 over the square root 5. We've got sine theta equals to 1 over the square root of 5, and therefore tan of theta will be 1 over 2, implying that, which is 26.6 degrees. Just a quick note here, positive definite quadratic forms. A quadratic form that is said to be positive definite, that is if this is bigger than 0. For vectors x where x is not 0, it's negative definite if that is negative for all non-zero vectors, and it's indefinite if that has both positive and negative values. Right, Theorem 2 just or Theorem 7.3.2 just states that if A is a symmetric matrix, then we have that this is positive definite if and only if all eigenvalues of A are positive. And also that is negative definite if and only if all eigenvalues of A are negative, and that is indefinite if and only if A has at least one positive eigenvalue and at least one negative eigenvalue. Okay, so I just want to make a remark, maybe just look at the proof of this first property. The other ones follow similarly. So that quadratic form, they say there is positive definite if and only if all eigenvalues of A are positive. So what we do is we assume that is positive for all non-zero vectors x, and let P again be the matrix that orthogonally diagonalizes So we can do a change of variables. We can change the variable. What we can do is we can solve the following. So if we take the vector y, which has got a 1 in the ith position and 0 everywhere else, then we can just find an x that will satisfy that change of variable there. And basically then we can go and write x transpose A x, which we know is always positive. We can write that as y transpose, where D is the diagonal matrix with all those eigenvalues on the diagonal, and that we know is that is basically lambda 1 times 0 plus lambda 2 times 0, and then you're going to get in the ith position you're going to get lambda I, and then you're going to get zeros everywhere. So that is going to be lambda I. So lambda I, the ith eigenvalue, is going to be greater than 0, and you can form this argument for all your eigenvalues, right? So basically you've just proved that all the eigenvalues are positive. Right, now if we assume that all eigenvalues of A are positive, then basically we have that this thing is always going to be this thing we know is going to be lambda 1 Okay, and basically look at this. These are all bigger than or equal to 0, and these are all positive numbers, right? By assumption. So this thing, this whole thing here, that thing is going to be bigger than or equal to 0. So we just need to show that it's strictly bigger than 0. Right, now if x is not 0, then if say y is 0, then we've got that x. Remember we said x is this thing, which is then going to imply that x is going to be 0. Okay, so thus y is not 0. Remember, we want to show that it's positive definite. So we need to show that whenever x is not 0, then this thing is bigger than 0. So if x is not 0, then y will not be 0. So therefore, hence, if y is not 0, then this whole sum here that we talked about, right? That is definitely going to be bigger than 0. Okay, so all the others work exactly the same. I'll just quickly determine by inspection whether the matrix is positive definite, negative definite, or indefinite. Now the first matrix, the eigenvalues, it's got one positive eigenvalue and one negative eigenvalue. So that is that's indefinite. Right, the second one has got two negative eigenvalues. So that is going to be definite, right? So that's going to be definite. And this last one is only positive, right? So that's going to be positive. Right, so if A is symmetric, a 2 by 2 matrix, then if this is 1, that represents an ellipse if A is positive definite. That equals 1 has no graph if A is negative definite, and this represents the hyperbola if A is indefinite. Okay, so it's pretty straightforward to actually prove that. You just need to go and write this out and verify that the equation is in fact that of an ellipse if it's given that A is positive definite, and the same for the other two properties. So here they just ask us identify the curve represented by this particular equation here. Right, so there we've got this equation, and what we want to do is want to use this theorem we just talked about. Okay, so we're going to take this function and just note that we can write that as that as this vector here, and we know how to do this, where that's a symmetric matrix. Alright, and then what we're going to do is this is my matrix A, so what we want to do is we want to look at the eigenvalues of that. Right, so what we're going to do is determine, we're going to determine and that should give us basically a clue. Right, so basically we do that by doing it the normal way, looking at the determinant of that. So that's going to be lambda minus, that is going to be minus, that's going to be lambda minus, and that is going to be minus. Okay, and we're going to look at the determinant of that matrix, which is basically going to be lambda minus 6 squared minus 16, and we are to get the eigenvalues, we're going to place that equal to 0, and from there we then obtain lambda so the eigenvalues they're both positive. Right, so thus A, according to the previous theorem, A is positive definite, Right, and this thing says that will represent the ellipse if A is positive definite. Right, so this form that we originally talked about, that we said is 2. All right, and that you can just interpret pretty much as, you can just interpret that as this. Okay, and that you can just interpret that as just basically another, it doesn't really matter, x prime transpose A x prime, okay. And basically, because the eigenvalues are, alright, so because the two eigenvalues are positive, A is positive definite, and so the curve is an ellipse. It's in fact to be specific, a rotated ellipse, because it's got a cross term xy. Right, so the last concept is just identifying positive definite matrices. Symmetric matrix A is positive definite if and only if the determinant of any principal submatrix is positive. We won't be looking at a proof of that. We can just quickly look at the following two examples. Right, so to show this, we have again that the first one, the determinant. If we look at this matrix here and we look at the principal submatrices, there, that matrix there, the principal submatrices, the determinant of first one is 2. Okay, and then the next principal submatrix is going to, the determinant of that matrix is going to be the determinant of the matrix 2 minus 1 minus 1, 2. Okay, so it's pretty much this matrix here. We looked at that matrix there, okay, and that determinant is 3. And then the next submatrix is the whole matrix there, so that is 15, okay. So that's clearly positive definite. Alright, next one, find all values k for which this quadratic form is positive definite. So there's my quadratic form, and that corresponds to this, right? And you can go and determine what A needs to look like. A is a symmetric matrix. And that matrix must look like that, and it's easy to determine that. It involves basically going and looking at when A is positive definite, for which values of A, for which values of K is A positive definite. So first of all, the determinant of that is 2. Then we look at the determinant of that, which is also positive. And now we need to look at the determinant of the whole matrix there. Okay. So let's go and work out the determinant. So there we've got the cofactor expansion, and that becomes right, and right, so what do we need? We need basically this to be bigger than 0. And that happens if and only if K is less than the square root of 3/2.